Alright, hey guys, what's going on? So today we are going to be talking about the infinite dimensional representation of the Lorentz group. So we're nearing the end of a large section of what we're talking about, which is sort of the mathematics behind modern physics, right? And then we're going to spend one or two videos on this, and then we're going to dive straight into the physics. We're going to dive straight into working with Lagrangians. Okay. So again, if you like this kind of content, make sure to hit that like and subscribe button. If you want to see content early, make sure to go onto my Patreon page where you can see this kind of stuff early. With that being said, let's get straight into the content. All right, so we are talking about the infinite dimensional representation of the Lorentz group today. So let's recall a few things. The generator that we have been dealing with, or the generators that we've been dealing with so far, are rotations and boosts. What exactly are rotations and boosts? Well, a boost is a change in an object's velocity, and a rotation is a change in the object's, not position, but orientation, if you will. So I wouldn't say position here. This is orientation, say. What we want to be able to So we want to be able to not just operate on these objects, right? Say it's a vector or a spinner or something like that. We don't want to be able to just operate on those guys. We also want to be able to operate on the space-time itself. And in order to do that, well, the space-time itself is a continuum. And so we have to find an infinite dimensional representation to be able to operate on the space-time. Now, this is how we do this, right? So we want to be able to operate on a space-time background as well, so we define this guy right here. Okay? And what we want to do is we actually want to show that this guy right here actually satisfies the Lorentz algebra. We found that the Lorentz algebra was this. Okay? I sort of just gave it to you as a given. Deriving this thing I don't think is super necessary. It's actually quite hard. So what I'm saying here is that this guy right here contains all of the generators, or the relationship between two generators, essentially, that obey the Lorentz algebra. So this is the Lorentz algebra. Okay? Now, I'm going to sort of do this in a weird way. We're going to go through an example to show how this is the case, right? So we take this guy here. Just take this guy for really quick. And we want to say, okay, we're going to put in mu equals 1 and 2 for this guy here. This is one generator. This is the other generator, generator 3, 2. These are infinite dimensional. And what we want to say is that this is equal to these two guys here times the 1, 3 component, right? And so the way we justify saying this is by saying, well, this was J3, this is J1, and this is J2. The way I sort of go about that is whatever is omitted here, whatever number is omitted is the generator that we're dealing with, because recall that Ji, we said, was equal to 1/2 ijk m jk. Now this is j and k, this is I. So if this was 2 and this is 3, this has to be 1. Right? So recalling this guy, we want this to be true. Right? So we'll J2, right, so J2 is M13 in the infinite dimensional space. And so we have 1, 3, 3, 1. That's how we're defining this guy up here. We have our I, we have our -1 and our I, and we get this. Well, so this isn't really a proof, right? This is kind of just, this is what we want to show, right? We want to show that this equals this. And we kind of just said, well, this equals this, and then we went through a tiny little bit of math here. But let's actually prove this. This is actually not too difficult. There's a lot here. But we'll go through this. This isn't too bad. So M12 and M32. These are their definitions, right? So 1, 2, 1, 2, 2, 1. When we have the subscript here on the partial derivatives, that's just saying we're taking the derivative with respect to x2, right? So I'll just write that out explicitly. Like this. And so forth. All right. So I just had subscripts, superscripts here because and here because it's just shorter to write. All right. So let's go ahead and do this. We're going to go through this pretty quickly. You can pause wherever you want, but again, I like to keep my videos short. I don't like to drag things on for too long. This is why I have this all pre-written out as well. All right. So M12 is this right here, this guy right here, and M32 is this guy right here, 3, 2, and 1, 2. Okay. And so this is a little bit misleading actually because we have the brackets here, but these two brackets don't denote a Lie algebra. These two brackets are just sort of encapsulating everything into each other. We have a dummy function out here as well because these are all operators. All right. So now, okay, what happened here? So we have I times I, which is -1, but with this makes it a positive. So this guy here, these two guys here essentially moved up this way, and we got rid of the i's. Same thing here, I and I is negative. Here's that negative. And then these two guys here are right here. All right. Now we distribute the dummy function. We can distribute the dummy function. And in distributing the dummy function, we distribute it again, right, into these two guys here. Then we have to operate, this guy has to operate on this guy has to operate on this guy. And when we do that, we're going to get, so this guy and this guy right here, so that's these two. And then this guy and this guy right here, well, that's these two guys right here. And you can see, okay, I'm not going to go through all of this again because this is pretty long, but you can pause the video and you could see how this plays out, right? Because everything sort of gets longer. Everything gets uglier before it's going to get nice. But this is what we get, okay? And then we start to see something here, right? So dx2, right? So we have to do the product rule, right? So the product rule. So the derivative of this and the derivative of this guy. So essentially what we're doing is this. We're doing product rule. Right? So when we do the product rule, we get this and this. All right. Where does this 0 come from? The 0 comes from taking the derivative of x1 with respect to x2. Well, because there's x1 is not x2, that's just going to be a constant, so that's 0. And you can see how this all plays out as well. And you can see, what you'll see is that the only thing here, when we have this guy, let's see here, so x3, and we're going to have these two guys right here, right? So we have dx, let's see here, dx, I'm getting a little lost here. All right, so here's this guy. So dx2 with respect to x2, right? So that's just going to be so that's just going to be 1, right? So we just get this guy, right? So yeah, so that's where that comes from. I was getting a little lost there. But so we just get 1, so it just gives us this guy right here, which is right here. And then so here, I'll write that out actually. So this is just going to give us 1. So in 1 times this guy right here, well, that's right there. So that's how that works out. And then we do that. We sort of go through the rest, right? So this time, the derivative of this now is the double derivative, right? And so you can see how this all plays out. You can go from this step up here to this step relatively easily, I think. If you can, again, pause the video if you want, but that's how that goes down. Now, here comes the fun part. We have all this, and now, okay, so x3 times 0, well, that's just 0. x3 times this, well, it's this. x3 times this, right here, x3 times this, right here. And that's all going to play out like this as well. All right. So here we're going to say something. If f is a function of all four of these variables, x0, x1, x2, x3, it's a function of all these four variables, and it's linear in all those variables, right? So we just have constants in front of them. This is what a 4 vector looks like. And so we have then our purple terms, these guys right here that I underlined in purple, these guys are going to go to 0, right? Because any double derivative, when we're looking at x2, say, well, the first derivative is going to be c. This next derivative is going to be 0. Right, so these guys are going to go to 0. All these guys go to 0 as well, right? Because we have a minus sign here and a plus sign here. So these two guys cancel, these two guys cancel, and these two guys cancel. What we're left with are these two guys. So this guy, which was way up here, right, is equal to this guy. Well, that's right here. So we've managed to show that this guy indeed works for this Lorentz algebra. And just by an example, right? So you can do this for, say, M13 and M21, say, and see how that plays out. That's going to play out the same exact way. You can use this prescription that we've done throughout this whole process, and you can get to an answer, and you'll find out that, again, this guy right here does indeed obey the Lorentz algebra. And so you might think, okay, this is actually quite illuminating. This was illuminating for me as well. This idea that this combination of derivatives and derivatives in combination with these position variables, these operators, actually, this is an operator. Everything we've been dealing with is an operator. Transformation is an operator. This sort of enlightens a few things, because it says, okay, we can have operators that are matrices, that are generators. But then what we're saying is that we have matrices, but we also have this operator here, which is clearly not a matrix, but it works. It works because when we put it into here, everything plays out, right? So we have, again, so this is our infinite dimensional. This is why we have this infinite dimensional generator. This generator, again, is this is a generator, much like the matrices we've been dealing with are generators. All right, so that's our infinite dimensional representation of the Lorentz group. So we have matrices, boosts and rotations, and now we have this operator thing that's a combination of it's an operator, and it's a combination of derivatives and positions, essentially. And again, this is our field. This is our space-time, right? 4 vector. You can think of it like that. Okay, so that's our infinite dimensional representation of the Lorentz group, and we are getting close. We want to talk about this a little bit more. We're going to put it in the context of Poincare groups, and then we're going to go into making Lagrangians invariant. We're going to find all the fun physics, the gluons and stuff like that, and the quarks that make these kind of things, that makes modern physics what it is. So with that being said, again, make sure to hit that like and subscribe button, and I will see you guys in the next video. Bye.